Hello, everybody. Welcome to the second installment of the series where we explain cosmic dynamics in a simpler level such that high schools can understand it. In this video, we're going to be talking about the fluid equations. Now, what are the fluid equations? They're equations that can model the change in density of the universe's components over time, uh, such as things like matter, radiation, and all that stuff. And these equations, we're going to deal with the thermodynamics of the universe throughout its evolution. So basically, thermodynamics back then and now, and how they relate to the things that I've talked about in the previous video. So as it's stated in the name, it's fluid equations. This one, we're going to assume that the universe is an ideal fluid. It's kind of different from last time's last time's explanation because for an ideal fluid, its components don't really interact with each other like with gravity. But again, this is just a consequence of this very simplified system. All right. So now we're going to talk about it. First, I'm going to talk about something called systems. Now, in thermodynamics, we know there are three types of systems: open, closed, and isolated. In an open system, matter and heat can exit or enter the system. In a closed system, only heat can uh, enter and exit. In an isolated system, nothing goes in, nothing goes out. So, because we know that the universe is basically everything is the universe, right? And if everything is the universe, then nothing is outside the universe. Therefore, uh, nothing can go inside of the universe. If nothing from outside the universe can go inside of the universe, nor can any particles from the universe go outside of the universe without being in the universe. So we can say that the universe is an isolated system. Now, why does that matter? Well, it does matter with thermodynamics. So we can see here, we know that the universe is an isolated system, so no heat goes in, no matter goes in, no heat goes out, nor any matter goes out, and that the universe is expanding. You can see it through lots of data, especially the ones about galaxies moving away from us that I've explained in the previous episode. So here's the model of the adiabatic expansion. You can see that the volume goes up and the pressure, this p-axis here, it goes down. So the volume increases while the pressure decreases. Not only that, but the temperature also decreases. And in fact, as a consequence of that as well, the density decreases as well. And how do you see it? You can even see it through this model right here. So back then, the universe was hotter. It had a smaller volume. Therefore, it had bigger pressure and it had more density. So billions of years ago, it was more dense. You can see more lights in the night sky, basically. But now it's colder, see less stars, and it's bigger. So what are these equations and how do you derive it? Right. So first off, we begin with the first law of thermodynamics. The change in internal heat is equal to work given to the system subtracted by the work done by the system. I can just switch to the W to the other side, and we get the work given to the system is equal to the change in internal energy, internal heat, plus the work done by the system. Or for a co-moving thing, for co-moving things, uh, the temperature multiplied by the change in entropy is equal to the change in internal energy plus the work done, or pressure multiplied by change in volume. We assume that the pressure is the same despite, like I said previously, the change in pressure of the adiabatic expansion. Uh, why is that? Well, we'll talk about that in a future episode. Now, because the universe is everything that ever was, everything that is, and everything that ever will be, therefore there's no heat going into the system, or Q or change in entropy are both zero. Therefore, we can say that dE plus PdV is zero. Now, we also assume that the energy is the rest energy of all its components. Uh, why can we say that? Well, another assumption here, as an ideal fluid, they don't interact with each other, so they don't really store energy in themselves, and they don't move at relativistic speeds. So it's just mc squared, or 4 pi over 3 ax cubic rho c squared. Now what is this? What is this ax cubic? Well, it's the things that you've seen in the previous episode. But if you've missed it, it's just the scale factor multiplied by constant distance that's dependent from time. And yeah, it's because pressure is constant, volume is 4 over pi third ax cubic. Okay, so we must also remember that the scale factor a is a function of time, and so is the density rho. They're both functions of time. Since we're modeling the thermodynamics through time, it's very important to know which are functions of time and which are not. So now that we've already declared all our variables and all the functions inside them, let's derive it. So because E is equal to 4 over 4 thirds pi, A as a function of time, multiplied by x, all that cubed, multiplied by rho times a function of time, c squared. Okay, since we're modeling the change in energy through time, well, we must derive this energy to time. So it's dE over dt. And because there is a multiplication of two functions of time, we must do the, the rule of multiplication. So you see here, because this is a function of time, and this is also a function of time, they must be separated like in normal derivation. So we assume these are constants, and so it's just basically just this divided by this divided by all these constants. And don't forget, this exponent is also a part of the scale factor. Because of that, we're going to derive them, the multiplication type, this here and this here. Because of that, we can derive that this density prime is equal to the change in density through time, and this scale factor prime is just the change in scale factor through time. Remember the law with exponents, the rule with exponents. And to simplify things, like in the previous episode, we're just gonna do everything that's derived through time as just that object with a dot over it. This density here and this scale factor here. Likewise, we can do with volume, which is rather similar to this part of the previous expression, very similar, only without the rho c squared here, without the density multiplied by the speed of light squared. So in order to save time, let's just use what was our d there, right here. Now that we've defined the change in energy and change in volume through time, we'll just add them all up, and remember that they are equal to 0. So let's just add them all up right here. We see this very long equation right here, but do notice that there are a lot of similarities between them, namely 4 over 3 x squared here, 4 pi over 3 x squared, I mean, x cubic, pi over 3 x cubic here, and they are both contain a squared. It's just a squared multiplied by a. So first we'll just take away all the similar things, the 4 pi over 3 x cubic first. So once we divide it by 4 pi over 3 x cubic, we can just factor out here parts that contain the change in scale factor is 2, and the part that doesn't have a change in scale factor over here, and we can just factor that in. Next, we're going to divide it all by a cubic such that there's no scale factor here, and we have the change in scale factor divided by the current scale factor. All right, and we've also factored the c squared out such that it's just rho plus p over c squared. P is in pressure, constant pressure. Now we move it to the other side and divide it by c squared, and we'll get that the change in density over time is equal to -3 times this change in scale factor over time divided by the current scale factor multiplied by the density, the current density, plus the pressure over c squared. And if we remember from the previous episode, the change in scale factor over time and divided by the current scale factor is just the Hubble's constant right here. So as an added bonus, we can kind of redefine the Hubble's constant, just divide it by this -3 rho plus pressure over c squared. And yeah, we found another meaning of the Hubble's constant as a function of density and pressure. So yeah, this is all for this video. I hope you enjoyed and learned something new. Thank you.